Hey everyone, I'm Brian. I'm the co-founder and CTO at Thunder Compute. First, thank you, Rob and Selby Jennings for putting this on. This is really cool. So, so today I'm talking about instrumenting your hot path in C++. So, kind of the goal here is, if you're super familiar with logging and observability, hopefully you can learn something new. If you're not as familiar and think like this is kind of a boring thing, hopefully I can show you there's a lot of really interesting stuff that you can do with logging. And yeah, so you can jump into it. So kind of a little bit about us, and to motivate the problem. So at Thunder Compute, we're building a cluster hypervisor for GPUs, and it's kind of a lot of terms, but this is kind of within the space of GPU virtualization. And really the main takeaway is that we sit between the application and the GPU. So that means anytime an application wants to use the GPU, it has to go through our runtime. For the purpose of this talk, what that means is that our runtime is directly on the application hot path. So any overhead that we introduce directly affects the application. So it's very important for us to make things run fast with low overhead, and we still need to be able to debug things. So that's kind of why we're talking about this today. Kind of one step further into how we do this. So we're building a CUDA compatible shim. So the idea is, with an application, whenever it wants to talk to the GPU, it has to go through an API, in this case, CUDA. So that's already some sort of middleware that sits between the application and the GPU. So what we can do is we sit at that same layer, so we can intercept all the calls that application makes to CUDA and send them across a network over like any sort of fabric. So this is InfiniBand, IPC, Ethernet, whatever, and then gets executed on a remote server process. Kind of biggest thing here, this is a distributed system, and it's pretty complicated. So it's like you can build a prototype kind of easily, but then like actually bringing that to production is where there's a lot of work that needs to happen.
So I just was curious. I noticed that you were saying that this is CUDA compatible shim. Do you actually have anything for SYCL, assuming that you're basically, your GPUs are not necessarily NVIDIA's GPUs, but maybe like AMD or any other type of GPU manufacturer?
Yeah, no, this is just CUDA. So same techniques, kind of same principle can be applied to AMD GPUs with ROCm, but CUDA is like kind of the dominant player in this space, so we support CUDA. But yeah, so basically, it's a distributed system, and if any of, I'm sure many of you have like dealt with and built distributed systems, there can be a lot of things that go wrong. So you can have either on one side of this, you could have like some sort of memory corruption, since this is like still low level, or you can have something that works across the system, where you can have like some kind of a distributed deadlock or whatever. But kind of the key is, in order to debug this and actually bring this to production, it's very important to have good observability and good error, like being able to like debug errors pretty easily. So that's why we had to end up building a lot of this from scratch. So yes, we need detailed logs, and we can't introduce overhead. That's kind of point number one. Whenever we introduce overhead, the application slows down, and people don't like their GPU applications getting slower. So, but yeah, so then next thing is, why do we actually build this ourselves? It feels like something that should exist. So kind of to start, it's the instrumentation problem, and like actually debugging this in production became a problem very early on. So the moment we like ship this to customers and users, we need to be able to debug their errors. So we can't like build a half solution here. It's like we kind of needed to build this full thing pretty early in the process in order to actually understand what was happening. And unfortunately, there were no good open source solutions that met the performance requirements that we needed. And we'll get into that. But a lot of typical advice is on the order of don't log that much and disable logging of some kind, which isn't really something that we're able to do. However, within large companies, there are, like, people have figured these types of problems out. And that's why it's very easy to underestimate, like, the challenge in building this. So at a large company, there's probably a team or like multiple teams which can manage these tools, and then the entire code is already instrumented. So kind of in that, there's like little practical advice online about this because a lot of that knowledge is within companies. So this is kind of like what I wish I knew jumping in before like starting a lot of this. But okay, so looking at some C++ code, since this is C++. Um, super simple logger, right? This is like most simple thing you can think of. Just do some formatting, print to the console, and that's it. Which this generally works pretty well if you're doing like a CLI, maybe like some sort of a REST API. But if you were to just put this directly onto like a critical path where you actually care about performance, like what would go wrong? So you guys just want to yell.
Well, would there be like some slowdown because it actually has to take the data that it has, the arguments that it has, generated timestamp, and send that to standard error. Possibly also, if there's any sort of slowdown to the logger, that might be also an issue that you might want to look at that. I think without actually measuring, that's probably the stuff that I would be firsthand.
Yeah, no, that's exactly right. I mean,
isn't there also sometimes problems with using spin kernel for benchmarking? And don't you also need to like warm up the stuff more? Warm it up.
Yeah, no, exactly. Yeah, so benchmark.
Just like do this, you have to have like a loop or something.
Yeah. So yes, for the benchmark methodology, yeah, you need to do the warm-ups and all that. But yeah, stood chrono, there is also a cost to like, yeah, to doing. We'll talk about at the very end, but it's actually surprisingly low because of some optimizations the Linux kernel already does. But there's still some cost and something that you can do to optimize it. But yes, that is a very good point.
Well, you already also, I mean, I think there are two versions of this of Chrono. Right now, you use system clock, which is the clock that's tied to the CPU.
Yeah.
That might not. I mean, if you're looking for something, you might want to use a steady clock to give you a little bit more robust timestamps.
Yeah, so I agree. I think in general, there is overhead in like getting the timestamp, and it is something we'll talk about, like how we can optimize that. So yes. Yeah, system calls are expensive. This is also, yeah, it could be like a synchronous thing. It could be like IO, because in this case it's standard error, but that could also be a file and network socket, right? So basically lots of things. Yes. Yes, string formatting, exactly. String formatting is very expensive. So, okay, I think we basically got most of the things here. So kind of like what we were saying, string formatting is expensive, both because of potential heap allocations and also the serialization cost can kind of add up. In this case, we can assume these are like uint64s, but if there was a floating point, there's like extra work that you need to do there. Like you guys were saying, writing to standard error, that could potentially be blocking IO, and it's synchronous. Wall clock, read every time. And then another kind of interesting one that this is something that surprised us a lot, but it's the storage requirements for something like this. If you were saving every single one of these messages and you were running it at like, say, 10,000 times per second, which is like a reasonable thing you can expect. And that's like about the numbers that we see in terms of CUDA calls per second. This is like about 100 bytes. So just over an hour, that's like 3.6 gigabytes of logs. And if you're like talking about hundreds or thousands of devices, that like kind of breaks down pretty quickly if you want to index this, if you want to query it. So the storage requirements actually were kind of the initial thing that prompted us to like have to figure out what to do a little differently here.
I was thinking that there might be also one more issue, and that is like basically you're just talking about what you're allocating and the size that you're allocating with the timestamp. That might not be that useful unless you know like how it actually went to that allocation. Is that allocation something that would, you know, what is a normal allocation, or did it do an extra allocation or something?
So you're just like in terms of heap allocation, what's the
right? I think,
yeah.
Like the idea is that you just are seeing the allocation and the size. That might not be useful. Maybe every time you're allocating maybe 75 bytes, and you know, and you really are not sure what that you know the address, but you don't know why is it doing.
I think I understand what you're saying, which is the heap allocation might actually be quick because it's using like some pre-allocated page already. And that's true. I think whenever I'm talking about performance here, I'm typically measuring tail latency. So that's partially what we care about. And I think on the next slide.
In this case, I wasn't talking about performance. I was talking about like just reading the message and understanding that why is it why did it actually create the message itself. If you're looking at it through just a log file, you see an address allocation and you see a size, but you don't necessarily.
Oh, okay. I see. You're talking about the message itself. Yes. So this message is just some junk, just as a sample. It's like you can imagine there's a previous call to like malloc or something, and then it returns the address size, and for whatever reason you want to log it. I think in practice this would actually be really bad. Like you probably shouldn't be logging something like this, but yeah. But yeah, so basically this is readable and simple, but kind of for all the things we've talked about, this is too expensive to do on like a critical path for all that. So instead, like what are the requirements that we actually need? So I feel like pretty obviously low performance overhead in the producer. And when I'm saying producer here, we'll talk a little bit more about like the producer consumer model for a lot of this, but this is the application. So it's the thing that's generating logs. We need that to be fast, and we need the predictable tail latencies, since it would be bad if like most of the time it works well, but then suddenly it just like hits you, and that's not great. Another piece is bounded memory usage, because you could just keep queuing stuff up, and maybe you could like keep resizing the buffers, but at some point, and I think this is a core feature of this type of a logger, is that the producer is going to be much faster than you can process these logs. So you can't just keep growing the memory. Otherwise, you're going to run out of memory regardless of how big your machines are. And then finally, I think this is kind of a more interesting piece, which is durability for important events. So if you collect all your information, it's like you run something for like 2 hours, nothing's lost except the one time there is an error, that's effectively useless. So what you actually care about is the fact that you get events that matter. So, and that kind of like it creates the design that we got towards. But it's like really the kind of this graph is just like a visual of that point. But the importance of a log, if you're generating a ton of these, it's like most of the time nothing, it's all fine, right? If everything's working great, you don't really need to debug anything, so you're good. But then when an error comes in, you can imagine suddenly everything around that log is very important. So after it, probably less important, but right before the log, right before the error, figuring out what caused it is very, very valuable. So that's what we don't want to drop. So, and I think many of you probably kind of see where this is going. But for those that are less familiar with logging, how a standard asynchronous logger would work, where even if you're writing to like an output stream, under the hood, it's fundamentally a producer consumer. Somewhere there's going to be some amount of queuing, something's producing it, and then something has to flush from the queue. So you produce some logs very quickly. Let's say this is producing at that 10,000 messages per second thing. You have a terrible consumer. It's not consuming anything. Then a new message comes in, F. So now what do? There's, and all these like and most open source implementations, there's really two options. Either you drop the message or you resize the queue. And neither of these will work for our requirements. Either resize the queue, you're going to run out of memory at some point. Drop the message, you're going to miss an important event. So yeah, this doesn't work. And it like really prioritizes what's already in the queue and making sure that's durable. But that's not what we really care about. And that's the trade-off that most of these off-the-shelf loggers make that doesn't work for our use case.
If you're assuming that your producer is very fast and your consumer is slower, could another approach be like having one producer and multiple consumers to make sure that the queue is relatively free at all times?
So yeah, I think you can come up with a lot of schemes on how you can make this consumer faster. You can have multiple consumers, you can do batching. There's plenty of things that you can do, but I think fundamentally, like one of the features of the logger here is that we are producing messages exceedingly fast, and we're gonna have to drop things at some level because we just can't consume everything. And I think in some instances, if you have like a huge machine that has almost infinite memory, a ton of disk space, then you could probably get away with just like throwing more hardware at this. But for a lot of our use cases, we're on like pretty limited hardware, and it's like very heterogeneous. So it's difficult to just guarantee that we can like keep throwing more hardware at the problem. But yeah. So basically, yeah, the solution here is just to have a ring buffer instead of a queue. And then the ring buffer doesn't actually function as the source of durability. Instead, it functions as the context around the log. So you can imagine you have a ton of these threads, and all they're doing is just writing to this ring. And they keep overwriting each other, which is also surprisingly not a common feature in most off-the-shelf ring buffers. Once they fill up, they just block. So what we actually want is just to keep overwriting. So the goal here is that this ring buffer is a fixed size buffer, and it effectively functions as like a snapshot of some previous amount of time. And that amount of time is basically however long or however big the buffer is. So you can imagine now, most of the time, nothing's happening. We just write to this buffer, and the consumer is going to sleep. But then once an error comes in, suddenly we actually need this information. So consumer has to wake up and do something. In this case, it can take that's basically the context around that error, which is the buffer, and that error message, and then it can flush that. So what we're doing really is limiting the amount of data that we're flushing.
Are the threads from the same producer or different producers?
So good question. These are right now, these are all application threads that we care about, and they're all just in the current state pushing to the same queue. Obviously, there's overhead to this, and when like we'll go through like optimizing this path, and one of the optimizations is around that, and we'll show like the improvement.
So yeah, question before you did this like buffer approach, you doing like off the shelf drops?
Yeah, exactly. So what would happen, like exactly, is like you can imagine for what we're doing, every CUDA function matters. So you start logging, it's like this function happens, this function happens, this function happens, and that happens really, really quickly. And at some point, you're just gonna have to start dropping these messages, and then 100 functions later, 1,000 functions later, an error comes in, and all you see is like a bunch of these useless functions, really. And that just doesn't work for us, right? It made debugging something impossible. And also, we would fill up our storage because we're just like streaming data. And once you start paying for object storage and egress fees, you start to feel how expensive some of this stuff can be. But yeah.
Yeah. So you mentioned with like traditional ring buffers, you're going to see like blocking whenever the buffer's still filled. Is this something that something that you were looking at in your particular implementation of you had a ring buffer that was doing this blocking, and was this like an issue of with timing constraints? Did you just not have proper, or did you have any like timing constraints that you were working with your consumers to make sure that you had a worst case scenario on those types of blocking scenarios? And was that just not enough, or what was like kind of is this like a problem of like how you time those things, like how much a consumer can do, like the worst case when it comes to blocking?
So are you talking about like that queue implementation when I mentioned it's blocking?
Yeah, like so in a traditional queue, whenever it fills up, it's going to block, right? And
yeah.
So like with your consumer, is there any way that you could guarantee some type of timing that you do have a worst case scenario when it comes to blocking, or was it kind of like a catastrophic thing where because you're like a distributed system doing all of these things, like, it could actually end up being like a massive Like, was that what you were seeing, like just massive delays?
Well, so we don't want to block at all. And I think that's kind of the, like, part of like the redesign is like how you think about this queue. I think in traditional logging things, if you like, you do something where you print the standard out, right? You're printing to a buffer, somehow that's getting buffered in memory, and then it gets flushed. Once you write to that buffer, there's almost a guarantee that it will get eventually flushed, versus that's not how we want to think about this. Instead, this is just context around what was going on for the previous 512 or something logs, which is like a proxy for maybe some amount of time. Then when the error actually happens, that's we like take that error and we can enrich it with all this context, and now we can debug it with like a fraction of the storage and performance cost. Yeah.
Oh, yes, so I was just wondering, basically, when the error occurs, you basically are trying to flush all of the data that's in your circular buffer or your ring buffer. Is there like a possibility that because you overrode some of the data, that maybe the exact cause of what was happening with your
Yeah.
with your program might have not been or may have been overridden?
Yeah. So
And if
that
so,
is
what's the problem?
that is a risk, but kind of the idea here is that's like almost a feature, because we do need to drop some amount of the logs, otherwise we're not going to be able to keep up. And this is just the way that we can get the most important information as reliably as possible. So there's always a trade-off here of, do you maybe just like keep buffering and hopefully it'll work and you'll catch the right thing, or you can just bank on the fact that if an error happens, it's most likely happened because of like some recently preceding event rather than something like way back when. And that's worked pretty well so far. It's kind of more concretely, like what we end up seeing is if you have like a sequence of CUDA functions, it's very possible that you accidentally manipulate some state many functions ago, maybe like 5, 10, and then that state shows up later on, and then something mismatches. So then there's an error. So as long as we can like track that sequence, then that gives us enough information to debug what happened. So yeah, I mean, I think I have a little animation, but basically, I think we kind of get the point here, where it overwrites old values, error comes in, you kind of copy this thing, that's a snapshot of the previous state, and then you can flush that. So, like, effectively why this works is now the producer rate is much smaller. The producer rate is just the rate at which you're submitting errors, as opposed to debug logs, which if you're sending errors at 10,000 logs, like messages per second, you're doing something really bad. So you can send a lot of debug logs, just don't send errors too frequently. And then all these other benefits that kind of we've been talking about, where keep the important context, memory usage is fixed because that ring buffer is fixed. And then really the performance we care about isn't the error path. The error path you can kind of understand is pretty expensive, but it's this debug log path. And that's fast. So now we can actually go into like our implementation. And for this, I will show some benchmarks. I'll show some code snippets. I'm not going to show everything because a lot of it is, I think it's like, now that you understand the idea, like the implementation of it is somewhat clear. So this is environment for all the benchmarking. I was testing on my desktop, which is an AMD Ryzen 9, has 16 cores. So all the benchmarks go up to 16 threads, because after that, the performance got worse. Bare metal Ubuntu 24, compiling command. I can give more information about the environment if you're interested. We'll show some flame graphs. Those are just with perf. And then for all the benchmarks, we do the warm up and then have 3 runs, 16 million debug events per each. And then we'll also show when 8 threads, all the flame graphs are with 8 threads. So we're measuring the per thread latency. So like how long on average is the write to a debug. So kind of this initial baseline implementation, which is pretty dumb, we're getting 580 nanoseconds per debug log. And we can kind of hone in on one part of this flame graph. And this is what we were saying before, whereas formatting is like all of this cost. So string formatting is just not the way to do this. It's very expensive for all the reasons we've been talking about. So the goal here is you want to switch to structured logging. So right now what's currently happening in that implementation is you have log debug, some format string, you have to format it, which that's the heap allocation and this serialization cost, and then push it to a queue. So how can we get rid of the string formatting? Instead, we should just do structured logging. So instead of writing strings, we write structs. Since this is a C++ talk, this is a very good use case for reflection. So we'll show some reflection code too. But this is it's a very nice and elegant solution to this, because now you want to like log an event, just create a struct and pass that in. So you're avoiding any heap allocation. This is fully on the stack. So that's nice. And also, you're not storing any unnecessary data. You're not doing any formatting on the path where you care about performance, and you just offload that to like some background thread where you don't really care too much. So this is what the application code would look like. You can imagine foo you really care about the performance of. So you can do this kind of the logging infra for this. There's a little more, but it's, again, very nice use case for reflection. But effectively how this works is you'll have a queue with like this fixed event, this event record. You can imagine we're still using the standard system clock, which we'll get to later. But you have a timestamp on every event. There's this function pointer for formatting, which we'll just talk about in a sec, and then just some byte array for the actual payload. Whenever you debug, we kind of erase the type of this original struct by just writing it to this buffer. Static assertion to make sure that your size isn't too big. Finally, you can create this event. This is the reason for this function pointer here is you want the specialization of that type for the formatter. So actually how you would convert this into a string, then you can just push that event to the queue. And like, you could probably speed this up by, instead of pushing it to the queue, you can write directly to the entry in the ring. That's one optimization, but this is a little more clear just to show. And then kind of the fun part is the reflection up here. So given this type, we basically just take this and can convert it into a string representation, that this is what will actually flush out to, if we do decide to flush this log, this is what gets shown. So it would be identifier and then just all the elements. So this happens on the critical path. Everything else happens in like a consumer thread, only when things get flushed. So offloading all the slow things to a background thread, basically.
So instead of using std string, could you actually kind of do a fixed, kind of create a custom fixed type or fixed size string and kind of use that for additional optimizations, assuming that your messages are not going to be bigger than a certain size?
You could also do that. That is an option. I think in practice, what we've seen is you tend to just keep writing new messages, and like it's very easy to just write something that's too big. So I think in practice, we found that just having these like structs tends to be a bit easier to manage. Yeah, but you could do it that way too. Both options are correct.
Well, I would say that you can't keep the structs for the member or the data function, but the messages to make it a little bit more readable. Probably you don't really care about like, having like too much characters or anything, maybe enough to specify what your function is. And then also, instead of using std format, just use the print function to print it directly.
Yeah, I think I see. And I think that is almost like a subset of structured logging, where you can imagine your struct, instead of it being a uint pointer and a size, it could be like a const char star, which is like pointing to static memory, and then some format fields. So, and like you could make the syntax around that nicer, so that instead of making a struct, you can make it look like a string, but under the hood, it's all going to effectively be something around this. So, yeah, that is a good point. So with that, it's about a 2.5x speed up. So now we're getting 229 seconds per debug, or 229 nanoseconds per debug log. So what's the next thing we can look at? So if we zoom in, can you guys see my cursor? I don't know. There's the atomic base. That's kind of the next thing. And this is what we were hinting at before, but kind of the best way to deal with sharing in a multi-threaded application is just not to share. So that's the solution, is don't share. So instead of having a single ring for all your threads, have a thread local ring. And this does reduce thread contention a lot. It does result in a few new challenges, and you're kind of breaking a few assumptions actually by doing this, but they're worthwhile trade-offs. So part of it is errors now become much more expensive to process, because instead of having a single ring, now you have many rings, of like depending on the number of threads, and you have to have some sort of a global registry. And then you also need to be pretty careful here with like static initialization ordering, because it's very easy to use something before it's initialized once you have thread locals at play a little bit. One of the things you're giving up here is cross-thread ordering. So if you have an application has like a ton of races, and you really need to make sure that the order between threads will show up exactly when you're debugging it, then you're going to start losing out a little bit, because now you're relying on the timestamp, and there's some instability with the timestamps. So you can't really guarantee cross-thread ordering as much anymore. And then finally, this is relatively small, but there's more memory usage, which you just need to be careful for. This is something Mark figured out at one point, where we were using too much thread local storage, and it was causing weird errors because pthread would like throw some weird error because we had too much thread local storage. So you just have to be a little careful about that if you do it in practice. So this sped things up very significantly. This was like a 12x speed up. So now we're getting about 18 nanoseconds per debug log. And there's one last thing, and this is the timestamp. So at this point, basically everything has been optimized except this timestamp. So what can we do? And it's kind of interesting. So I didn't know too much about this before, but the Linux implementation for timestamps is actually super optimized because of this VDSO. So that's like this virtual dynamic shared object, which gets mounted into every process. And the actual implementation of getting your timestamp doesn't involve a system call. So it's not terribly expensive. It's fully in user space. And one possible implementation of how this would get implemented, not saying this is how it is implemented, but the user space implementation of this would read some sort of a hardware counter and then perform some kind of a correction. So read that and then correction. But we don't really care about this correction for our case, since the timestamps are already like kind of iffy anyway, and all we care about is the ordering. So in our main thread, we might as well just read this hardware counter. So on x86, there's the RDTSC instruction, which can just read. It's like a UN64 incrementing counter. So we just store this instead of a timestamp in our structured log. And that does speed things up a bit. So yes.
Yes, you said that this was only on x86. Is there, if your machine did not have an x86 processor, would there be something similar on different
Yeah,
CPU architectures?
I would imagine yes, since it is just it's like the clock speed basically. So it's just like a constantly incrementing int. I'm not as familiar, so I can't say for sure, but I would assume yes. I'm sure someone definitely knows. But yeah, but yes, with that, we're able to get about a 40% speed up, which is pretty interesting. So just avoiding that correction. You can do the correction sort of in a background thread, and you can imagine an approximation would be something like count the number of clock cycles that like a sleep took, and then normalize that to like some baseline. It's not perfect because of like frequency scaling and all that, but it's good enough for what we care about, and the ordering stays consistent. So it's generally good enough, and it's worked for us in practice. So that's kind of the Hmm? So that's a good question. We no, so no, and I can explain a little more why. Uh, with RDTSE, it's one thing that's kind of important is we're using this P variant, which basically what happens is your RDTSE, it could get reordered potentially. So with P, you're guaranteeing there's a barrier afterwards. So what this does is within a thread, it effectively acts as like ordering guarantee. So you can't have two events in the same thread show up out of order. And you know that this is always incrementing. So within a thread, everything's going to maintain the same order. Where it does break is if you're using timestamps to like precisely track cross-thread events and potentially, like, I haven't talked about it too much, but we have two systems here, right? We have a client machine and then a server machine running across a network, and they're both emitting these logs at the same time. But like at that point, trying to do like nanosecond precision timing on hardware that we don't own is generally already, I don't, maybe there's a way, but I don't think it's possible. So what this really gives us is ordering guarantees, and from that we can debug most of it. And like it's precise to like some degree, like to the nearest like millisecond at the very least, which is generally enough for us to figure things out.
Yeah, so I get how you get ordering, right? But how do you go back to, I don't know if that's the question you were asking, but like, how do you get back to human readable?
Oh, yeah. Okay, so, sorry, I might have glossed over that. Basically, you can just do some kind of a calibration. So when the program starts, you can get the actual wall clock time and then sleep for a second and then look at the difference in time. And then that's your baseline. And it's not perfect. Like it's a very, very crude approximation, but it gets the job done to like, yeah, it's close enough. And like, sure, you'll be off maybe by like after a few hours, it'll be like a few seconds. But
And you said that you had like a parallel logging system that you correlate, or did I?
yeah, so what I meant by that is if you all the way back to the beginning, like our architecture diagram, there's these two components. Both of these are emitting logs using the same system. We don't correlate based on timestamps, but we were never really correlating based on timestamps. It never worked well enough because if we were to try to do that, you would need super precise things, and that's just not good enough. So instead, we use other like attributes. That's much more reliable. Yeah.
When the consumer is actually flushing this, is it not getting its own, like pulling the wall clock on the consumer side to actually do the flushing and like have timestamps there for like its relative time? I guess that goes back to my original question about like even if you're doing this to not block, the blocking characteristics of like the speed of the consumer, right? Is there a massive delay between, like, what does the delay look like between all of these, the producer filling up a ring, getting an error, and the consumer actually flushing this out?
Yeah. So, so you're basically saying, what if we just took the timestamp in the consumer?
Or is it even like, are you producing timestamps from the consumer?
So the consumer timestamps don't actually provide that much information, since what we care about is at what point in the application was this log produced. So you can imagine like you have like a bunch of events and like you have a log and then like something else and then another log and then something else and another log. If we did this all in the consumer, it would snap it at once and all of these would have the same timestamp. Versus what we actually care about is that event A happened before event B and then before event C. So that ordering is really what we need to preserve and not, yeah.
When you're testing these, were the threads linked to a particular core, or they were just free to?
They were just free to roam. It wasn't the most rigorous benchmark.
I was just wondering the effect of the whatever register you're reading has to do with
yeah. No, that makes sense. That's a really good question. I don't know. So I will look that up. That's a really interesting question, though. Yeah. So.
That was actually the internet. A guy in mine was asking the same thing.
Okay.
If the counters are stable across cores or.
Yeah, that's really interesting. I don't know, but I will look into that. So
this might be a little bit more kind of like an edge case, but does this also handle leap seconds? If you're looking for like highly accurate logs, something that might be happening at some point in time where you kind of get rid or added another second to handle
leap second, like a leap year, like when they add like that. No, we're just using it's a very crude approximation. So like, it's very possible that the wall clock time that we generate could be off by like a second. So basically, these timestamps should not be used as like the source of truth for what time something happened. We just care about the order. Yeah.
Just wanted to also check out you when you were kind of designing this. Did you kind of also contact Howard Ennett? He was one of the authors of the Chrono library to kind of look at some other optimizations for the following timestamp.
No, we didn't contact him. But I'm sure they have optimized this very well. And for a general standard library, they make the correct set of trade-offs where 5 nanoseconds doesn't, like, for a standard library, 5 nanoseconds is generally, I think it's okay, and it's the right trade-off to make here for more precise timing. Versus for our case specifically, we are willing to make this trade-off that the time is going to be imprecise. So I think that's kind of like one of the core themes here. There's like some very strict set of, there's a bunch of assumptions that are being made in a lot of these like standard tools. And if you're just like willing to break them a little bit, then you can start optimizing performance. So any other questions before I move on? Cool. But yeah, so either way, final result, I think it's mostly pretty what you'd expect, where x-axis is number of threads. So up to 16 threads. After 16, it becomes wonky. But basically, first two solutions don't scale well with threads. Second two, when it's like local, scale much better and are generally faster. This gap, so this is the not thread local, y at one thread is the thread local faster. And that's because the atomic integer that we're using, we have like stronger memory ordering guarantees, which you don't need if it's thread local. But there's probably a faster way to implement this. I think there's very likely a way to make it so that this is the same performance at one thread, but the behavior over number of threads should be the same.
Yeah. Just was wondering, right now you have a hard limit at 16 threads, but if you had like a much more like or more cores in your machine, would like the ring per thread and the ring per thread, would they kind of be in the same ballpark, or would they kind of oscillate a little bit more?
I would say that it would be much worse to have one global ring, because right now I have 16 cores. There's like a single NUMA zone. So you can imagine if like this scales to like multiple NUMA zones, if you just like blindly put one ring, that could be really bad if everything's trying to write at this at the same time. The only reason I have 16, it's 16 cores is the number of cores my computer has. So
okay,
that's
so
16.
So basically, you cannot, right now, we cannot really do any sort of assumption unless you've got like another machine that was a little bit more powerful and had more cores on it.
Yeah, you would definitely need to benchmark it. I'm kind of speculating here what it would look like, but I think this behavior, like the pattern, would be pretty similar. I don't think it would be as linear once you scale the number of cores as it is right now, but I think the general behavior would be the same.
Another question. Do you have any opinion on tracing versus logging and
Yes.
C++, open tracing or open telemetry?
Oh, I do have very strong opinions on this, actually. Yes. Okay. Tracing. I can start tracing versus logging. I found traces not to be as helpful as you'd expect them to be. Um, it seems like the perfect solution to everything. It's like, okay, you can see the full call stack, but I think in practice, there's just so much information and it's really difficult to trace, ironically. Um, and it's much more expensive to store. And it's like less intuitive to use also. Like when you see the logs, it's very clear, like, okay, this is where something might have gone wrong. Maybe I'm not using tracing as well, but I do prefer logging. Metrics, it's like, if you're familiar with observability, kind of there's three pillars. It's logging, tracing, and metrics. Metrics, I do really like, and metrics you can do very similar optimizations. Uh, we don't have time to talk about, but all the same tricks, I think, apply. And generally, off-the-shelf metrics libraries do much better compared to logging. Open telemetry. I have a lot of opinions about the open telemetry C++ SDK. Painfully slow. And the whole reason we had to build this in the first place was because the open telemetry SDK is absurdly slow. It spins up a ton of threads. It does a bunch of allocations, like at every single log. It's very general purpose, but for like hot path logging, it's too slow. That said, the open telemetry infrastructure is very good. So I would not instrument your code using their SDK, but it makes a lot of sense when you're actually flushing your logs. Because we haven't talked about this at all, but like after you flush the logs, they need to go somewhere. So you can either write them to a file, you can write them to standard out, or you can send them over the network to like some kind of collector. So it does make a lot of sense to use OpenTelemetry as this collector component. And it's an open standard. It's just like they have a gRPC and REST API. So you can write a custom serializer. AI is actually very good at that too, just to read the spec for that. So in that flushing step, yes, you can send it to OpenTelemetry. And I do think the OTel collector is very good. It's very good, just not the SDK.
This might kind of be something, but when you're are like tools like UndoDB also kind of useful for debugging, or is that just something that's beyond the kind of scope when you once you get the logs or something like that?
I'm not familiar with UndoDB.
Okay.
Is it like a collector component? Or?
So basically, I think from what I understand, it's basically a little bit of a debugger, but instead of like you can get your error conditions, and from that error condition you can go backwards and kind of understand how you got to that error condition.
So I think that's all like a separate piece, which is once you have these logs stored somewhere, you need to process them. And there's a lot of very good tooling for that. I think Grafana, ClickHouse, Datadog, like whoever you want to use, there's very good tooling for once you have these logs stored in a database somewhere. But what we really care about here is how do you get the logs out from the application to that database. So that was really the main goal here. And I think that might actually was probably worth saying, but like that's how like all these tools sort of play together. Yeah, I mean, that was main topics. If I had to like take away everything in a single sentence, it's like if you intentionally weaken some of the guarantees around like durability and cross-thread ordering, it does give you a lot of room for optimizing. And I think that can generally be applied to like many different things that you build. So I think the 3 bullets are like, again, they're like, they can apply to a lot of different things, but like do as little as you can on the critical path, defer as much work as you can, just something where you don't care about the performance, and then only really flush context that matters. So yes, that. Oh.
You adjust the size of the link.
No, so it's fixed size, and part of the reason we do that is we don't want any memory allocations happening, and it's you could potentially resize it if like during the application you see that it's really bad. But I think what we have found is just something that's relatively big works well enough for us. And that's just something that we like tuned over time. I think it definitely depends a lot on the application you're running. And if you're building something else, you might want like a bigger or smaller size. For us, with like CUDA functions, we have like every CUDA function logs like some number of logs in our application. And then we found that like the distance that one function can affect another function is also bounded. So like those two factors, if you just like multiply them, that gives you some approximate size, and we've just like fixed that size, and that generally gives us enough context. We err on the side of making it bigger so that we don't lose logs, but that's also like a trade-off there.
So that goes with my question then, because you were mentioning you were having bugs with like thread local memory, especially like large amounts. I assume that you were like dynamically allocating, and that's where like a lot of those issues came in. If you're doing like static allocation, or at least allocation like at initialization,
Yeah,
and then just like using that fixed buffer, can you go into like what are those particular issues that you're getting from your thread local memory?
Yeah. So I think the problem, if I remember correct, Mark might. I think Mark will know this better because he was.
So yes, you're correct. The buffer is so the big root buffer that is dynamically allocated. I mean, it's allocated once, but it isn't heap memory, so it does not take up like thread. The problem is at the time, at least, the way that our like some of the other. So remember, we are building a library that gets linked into third-party applications. So this has to handle applications that are doing lots of weird stuff. Yeah. And one of the things that they do is they launch new threads using the pthread API. And one of the options to the pthread API lets you select the stack size for the thread that is being launched. And at the time, our struct that contained the ring buffer also contained the random number generator struct in C++, which contained several thousand bytes of like the struct is several thousand bytes long, and that was being stored on the stack. And there was also some other structs and thread local things outside of our logger that were also thread local. And node.js, when it starts up, it launches pthreads with 32 kilobytes of stack space, and those threads were failing to launch because there wasn't enough space in the stack to store all the thread local variables that we were allocating. So yeah. So it wasn't actually that, but it's not actually the buffer, but it's more like if you're making an library that's going to get linked into any application, and you have a lot of thread local stuff, you might end up not having enough space.
Yeah. There's a lot of.
Are you guys using like fixed size elements in the ring, or do you try to work like some kind of variable size?
Yeah. So we use fixed size, and that was kind of in like that code snippet with reflection. That was sort of the idea is you can have like all these different structs that have different sizes, but you just create a single struct that has like a blob of data in it. So just like some buffer and one element that says what the type of that is. So it's like meta typing almost. But then the benefit there is every element in the ring is fixed size, so you don't have to deal with different sizing.
Get into like let's say like certain messages that you really need like a lot of you need that extra space, but you don't want to grow the ring for like every use case.
Yeah. I don't think we've encountered that, but that is definitely a possibility. Depends like how much information you want to put into a single message, I think is the trade-off. But yeah. Cool.
So your consumer needs to learn that I need to grab the ring buffer right now. That's kind of a separated channel, or how do you a lot of work go into that too?
Yeah. So it is a separate channel. And in general, like we haven't talked about that all that much. And reason for that is the performance for it is not as sensitive, since that like sending the message only happens on an error. So like if an error happens, it's kind of like something's probably wrong. Maybe like something in the infrastructure broke, there's a bug. So that should happen rarely enough to where we can just like eat the cost and like do something a little less optimized. So like I think, I don't remember exactly the implementation, but like you could think about using like a condition variable or something like that for this. Yeah, so yeah, when like an error happens, that can go through a separate path, and then it needs to take a snapshot of that ring. So um, you can imagine at that point it can hold a lock. You can do like more expensive operations. It's less important that that's super fast. So does that answer question sort of? Or
Yeah, maybe it's like it could be its own problem. Supposed to be telling you
yeah, so that's true. I think one of the assumptions we've made here is that there is no just like completely like it's not like we wrote to memory that we shouldn't and like potentially like seg faults. Um, that does add a ton of complexity. You're right, and at that point it's just best effort. So if like a seg fault happens, we like do whatever we can to like extract logs, but you can't be perfect. Yeah.
Maybe you mentioned it already, but how are you detecting the errors when you're pushing into the queue?
It would be so the errors is like it's like an app in your application. You're saying you like read the return code from like some call and it's not what it should be. So then you have like a log error function call. So like in your code you write like error, and then at that point, I I believe we do it synchronously at that even. It's like when an error comes in, you can just start holding locks on different buffers, take the snapshot, and then like write it to the consumer. Um, so I didn't talk too much about it because it's less sensitive and you can use off the shelf things for it. Um, but yeah.
So, what do you mentioned earlier? Like companies already have their own solution for it. Is it like the same as yours, or like how does it differ? Do you know anything about that, or?
I'm honestly not sure. I just know that a lot of companies have frameworks and they've already instrumented like all of their code, and it's like
It's like, yeah,
yeah,
what does NVIDIA or CUDA do? Because like I'm sure they need to know this stuff
yeah.
too. With their
So with CUDA, how I how I believe they do it is they disable logging for like whenever by default it's running, and you can enable it using like environment variables. And then they also generate like the super detailed crash report with like a ton of information that you can send to them. Um, NVIDIA also has like a massive QA team, and we're like a small startup. So we kind of have to be a little scrappy too with how we handle this. So we do our best. Yes, we are growing, and that's the last slide here. But but yeah, we have to like do what we can to, figure out when bugs are happening. So yeah, I will.
Like, kind of following up on that question, like, are you using this log system to debug like the whole system level errors? Because I know one thing a lot of the big companies do is you just have network tabs on every node.
Yeah. So we use it to debug our like that client and server process. So like the CUDA shim and then the thing that the CUDA shim is talking to. That's where so like that data path specifically is very latency sensitive, um, which is why we needed to build all this out. So this system we built specifically for that. For like all the other components in our system, like there's plenty of other things we use at that point, mostly off the shelf things. It's like you have different ways to scrape logs from like standard out of pods. That's all mostly standard. But yeah, we use it to like debug the whole thing. Exactly. So you could install a network tap, but then you get this problem with storage. You're going to be generating a ton. And I think a lot of people here probably have trading backgrounds. I think trading, there's kind of two things going for them. One, they have a ton of money, so they can just like, buy like spend like hundreds of millions. I don't know, but like a ton on storage, and it's like whatever. And then two, the trading day is like 8 hours, or it's like some fixed amount of time. So at the end of the day, you can kind of just like nothing has to work past 4:30, right? It's like if your thing seg falls, like once the market closes, it's fine. Versus we don't have that luxury. So just like putting network taps and storing everything will get really, really expensive. And it's also really difficult to debug and like actually query effectively.
I just was wondering, basically, from what I'm seeing, that you're basically keeping track of a lot of the compute resources. However, are there cases where some of your some of the issues might not necessarily be with like the compute issues or code issues, but maybe like some of the CPU, CPU or GPU heat distributions that maybe like that's causing some errors because you're generating too much heat and you're not cooling it enough to dissipate any sort of static problems.
Yeah. I mean, so there's kind of two classes of errors. I think one is bugs in our code, and two is just infra related. So one infra problem could be the GPU overheats. We actually have dealt with GPUs that just like NVIDIA has this thing called an XID, which is their term for like some sort of a GPU fault. And we had this one GPU in like a data center that would just keep throwing this like unrecoverable ECC fault. And it's very painful to debug, but that's just like one of the error modes. You could also have like network outages. Networks tend to be pretty flaky. So infra problems do happen, and this does work for that too. Because like in the case of a network outage, you have your client server. We have like some mechanisms to detect like something's not coming back. So when something's not coming back in our code, we have like some initial warnings. And then after a certain point, we're like, this is probably pretty bad. So then we log an error, and then it goes through this standard path.
Oh, okay.
But
So,
yeah.
but that's only for a network. That doesn't necessarily, track any sort of issues with like any of the hardware.
So yeah, hardware would have similar things where it's like a similar thing where like at some level, something will return an error. With networking, it's that things are like timing out. Maybe you get like error codes getting returned. With hardware, it could be that like this CUDA function just completely failed for like some reason. And at that point, we just have to log, and it's kind of on us to figure out. So I think like the main thing with errors, it's something actionable on our part. So we need to figure out what happened. And in order to do that, that's why we want all this context. Because like in the case of a hardware failure, you look at the previous functions and you're like, everything looks perfectly healthy. So this must be a hardware failure. Versus if it's not a hardware failure, where it's like something in our code, we'll very likely see like, oh, this thing got this really weird argument, for example. So yeah, we just check. There was some other questions, so I want to jump to those. But
you said that this was primarily for the communication between the shim and
the server process,
server.
yeah.
Why is it getting from client code then?
So you're saying like why do we?
How is this ending up in like the client's code if it's two components that you guys make?
So the shim, it's the shim piece of this.
Shim is part of the.
So the shim, it's a library that sits on your machine, the same way that libcuda would sit on your machine. So it's all the information on how to talk to the GPU is in libcuda. All the information on how this protocol works from the client side is in our library. So when someone starts running a process, it can be whatever, right? It could be native CUDA code, it could be Python, it could be some JavaScript framework, some like it could be anything basically that uses the GPU. And whenever they call CUDA, that's like where our job starts. So.
I'm curious how the reduced durability what portion have everything you need for
At this point, I'd say like 99% of the time, we're pretty certain. Definitely was not the case, which is why we've been thinking about this so much and why I think it's so important and like a very undervalued thing in infra. But yeah, at this point, it's like the logging is really good. So when an error happens, we know about it and we're able to debug it. And then like another kind of side benefit is with like AI, it's great at ingesting logs. So like when a bunch of errors happen and like you can query these logs really quickly, you just like say, what do you think happened? And it can like pinpoint something. Like oftentimes it can just like pinpoint because it's usually something super stupid. It's never something like, rarely it's something smart, but most of the time it's like something stupid.
Yeah, I just was curious. What I noticed that you used the C++ 26 reflection, but what about like using the sender and receiver protocols to maybe kind of deal with some of the GPU? And also, have you ever tried to, or did you ever have something like CUDA kernel system panics, or and how did you kind of debug those?
Yeah, so there are one case where this does break down, and like there isn't really all that much you can do. Is if like the node just completely fails. Like if you're running this thing and then the kernel panics, and like the Linux kernel, not like the GPU kernel, like there's really nothing that you can do. Like you can't extract any information. So at that, like that's rare enough to where if that does happen, like there should be a ton of other warnings. Like suddenly this node is not healthy, and like network traffic to this is not happening. So now we will see it in like another format, not necessarily from these logs. So I think that's actually another important part. It's you can't just like have this in isolation. You need like other observability. Like this is for this one very specific hot path component where the data path has like a lot of latency requirements, but that's not the only logging we have, right? We still have a ton of infrastructure monitoring, node health monitoring, all that, which that's a much more built out space. And there's a ton of tools and like open source, or you can pay someone for it. Yeah.
So within that ring buffer, we have the sequential.
Yeah.
I was wondering, how do you go about declaring kind of causality between threads? You have the approximate types, but you have heuristics that you
Yes.
can thread and okay, this thread kind of invokes something on this other thread and sometime later.
Yeah, that is a very difficult problem in general. In the case where there's no synchronization at all, then it's like it's on you to figure out. Like you have all this information now, and you know what error happened. Like it at least points you to the code that you should start looking at, and like then you can try to reproduce it. Other times it's like if you want to try to figure out causality between threads, if you have barriers or like some form of synchronization between threads, that's still ordered. So if you have like thread A that does something and then it does some kind of like a synchronization with thread B, because like of the timestamp we're using it's synchronized, that can't get reordered. So that will be sequential. It's more like if you have just like a pure, like in the purest form, like a race where two things are just going at it, then it's kind of on you to look into that. And that is a trade-off. Yeah.
Are you ensuring visibility on the consumer side from the snapshot using acquire release semantics?
Visibility on the consumer from the snapshot, you said?
Yeah, how are you publishing the snapshot?
Oh, so for that, we use, I believe it is acquire release. But with each, like you can honestly do anything. Like you could even use relaxed if you really wanted to, because what if you did relaxed, what it would mean is that just some of the oldest logs in that ring potentially have gotten overwritten. But this is already being used as like a heuristic anyway. So, but yeah, kind of like whatever you're willing to make like the trade-off. If you want all of the logs to get like frozen when an error happens, then you probably need acquire release. If you don't really care all that much, then you can do something more relaxed.
Yeah, so I know you mentioned that the system is pretty reliant on errors being rare, but I'm just thinking if you have maybe like a burst of errors, right? Since you're first,
Yep.
And you said you have some synchronization that happens at the point where an error is detected. Is there a case where some of those earlier errors can override the older errors, or that?
Yeah, I mean that's a really good question. So you're saying it's like you have an error come in, you snap this, and then another error comes in. Like, are you going to snap duplicate information? Yeah. Yeah, I mean, that's a really good question. So how it is implemented is you won't duplicate messages. So like when that snapshot happens, you also just flush that. Because duplicate messages honestly are the more annoying thing because that could like mess up what you see. Like you see this thing printed twice. I think luckily I do think a lot of like visualization tools actually handle something like that because messages have IDs, and if you're writing the same ID to a database, then probably is going to be like something's happening. Yeah, because like a lot of these things like on the back end are like Postgres or something like that. So many of them handle it, but yeah, we generally are somewhat careful. Any? Yeah.
Yes, I was just curious, like, latency might be an issue. Have you looked at some of the solutions or some of the techniques that are explored in the C++20 or C++ low latency study groups for like inspirations on kind of how to solve some of your problems?
I think likely have stumbled onto those threads as we've been like researching things. We do use as much off the shelf as we can. For example, there's like very good lock-free queue implementations that are open source, and like we can use those. But then there are these like missing pieces, and that's kind of where we have to build things out ourselves. So. Yes.
We have one question which I received by a tech from why did a hat say LD preload on them?
Oh, good question. LD preload is the mechanism we use for injecting our shim. So if you're familiar with the Linux loader, it's basically the program that takes your executable and actually like it starts it into a place that it can run, and it links all these dynamic libraries in. So if you ever ran like LDD on a binary, you see there's like a ton of these dynamically loaded libraries. That's like what gets resolved by the loader. And LD preload is a option that you can set on the loader to inject your own library ahead of a bunch of stuff. So it's a very powerful mechanism. And if you've used like Valgrind or like JE-malloc, or not JE-malloc, you can inject with LD preload. But like Valgrind, it's like LD preload under the hood for malloc and free and like a bunch of these libc calls. So LD preload. Any? Yeah. Yeah.
I was just thinking, so it was building this shim that is injected with LD preload. I call CUDA malloc, it will go through the malloc.
Yeah, exactly.
Right.
Mm-hmm.
I was just thinking about this. Like, let's say I'm calling CUDA malloc, I need to put in an empty pointer.
Yeah.
Right? And that is now going to your virtual GPU. That's going to give me like another pointer unless I come back. But that pointer has no meaning on my client side.
Yeah.
So
yeah.
Do you like map them? Do you like come up with a fake pointer to give the client? I don't know. I just was thinking. It's really unrelated to logic.
Yeah, I mean that is a great question, and that is the problem. Yeah. So yeah, no, I mean you hit the nail on the head. It's like, yeah, you need to somehow map all of this. So that's where a lot of the work that we have to do comes in. And very nice segue. We are hiring. So if you're interested in systems problems that we do way more than just logging. Logging is just a thing that I think is like generally applicable to a lot of people. But yeah, we do a lot of cool stuff. Send us an email if you're interested, founders@thundercompute.com. Me or Carl will see it. Let us know that you were here. But yes, those are the types of, that is a big problem that we need to figure out. So. Right.
Just maybe one last question,
Mhm.
but just kind of what's kind of the infrastructure that your GPU and your compute and kind of your storage and your operating systems actually exist on? Is it like Azure, Amazon Web Services, or is it something more internal?
So it can run on any Linux machine, basically. Yeah, like any, I think most Linux distributions will work. our infrastructure specifically, we have to go to like generally kind of more like random data centers to actually get GPU capacity since it's really scarce right now. But under the hood, they just give you a VM that's running like Ubuntu 24. So we can run our stuff on top of that. And like part of the benefit here is it's like in user space, right? So it's like super easy to set this up on a new machine. It's not like you have to like reconfigure the hardware or anything. You just like take standard hardware that has to have like relatively fast networking, which in a data center, that's usually the case. And then you can run this. So, yeah. Cool. I think that's all the questions. Oops.